All right, we're going to be doing basically all of chapter 12 in this video, but it's a pretty short chapter, so I don't think it's going to be overwhelming. We're going to first remind you guys about linear equations. All right, linear equations, you've seen these a lot. The graph is a line, and the equation is of the form y equals mx plus b, where m is the slope and b is the y-intercept. And if we're thinking about those things graphically, the y-intercept is right here where it crosses the y-axis, and in this case, it's going to be 0, -1. And I know that because I'm looking at the scale, and here's -2. So that must be at -1. And the slope, so the y-intercept is, this case, 0, -1. And the slope, let's just pick two convenient points. Let's start there and maybe go to here. It's going to be the rise over the run. All right, well, this is going to be 1 here, so we're going to rise up 1, 2, 3. So we have a rise of 1 for a run of 1. A rise of 3 for a run of run. So the slope is 3-1. And we know that's positive because it's going up from left to right. So the equation of this line is y equals 3x minus 1. All right. Hopefully that was a quick review for you. You've seen this before. Let's do a story problem where we use linear modeling. A taxi costs $20 to get in and 50 cents a mile. Whenever you see something about a fixed cost plus some sort of a variable cost, usually that's going to be modeled by a linear equation. We're going to use C to be the total cost. That's the dependent variable. That's going to be the output. And the miles traveled is going to be X. That's going to be the independent variable. Our model for this equation is C equals 0.5X. So 50 cents times each mile plus $20. So that's a linear model for this equation. Let's try another example. Ethan repairs household appliances like dishwashers and refrigerators. For each visit, he charges $25 plus $20 per hour of work. So I would like you to pause the video right now and do the following things. These are a little bit out of order. Actually, this should probably be the first thing you do. Identify the independent and dependent variables. Then second, write down the linear model. Third, think about what the y-intercept is and what does it mean in the context of the problem. And this should say, what is the slope and what does it mean in the context of the problem? So go ahead, pause the video, define your variables, and write down your model. All right, are you back? Well, I'm going to use C to be my total cost of his visit. And maybe this time I'll use T to be the number of hours he worked. So I've defined my variables, including the unit. So total cost, that's going to be in dollars. And number of hours he worked, of course, that's going to be in hours. So my linear model is C of T equals, well, it's going to be, and you can write this in either order, $20 per hour plus 25. If you wrote down 25 plus 20t, that's fine too. Those are the same. I just prefer the first one because it looks a little bit more like mx plus b. All right, so I've written down my linear model and I know my independent and dependent variables. What is the y-intercept? Well, in this case, my y-intercept is here. It's 25, right? That's the b value. And if I plug in t equal to 0, I get 25 out. That means it's also my y-intercept. And that's his fixed cost, right? That's how much he charges no matter what. What is the slope? Well, the slope on this one is 20 to 1. We can make that into a fraction. And the units are going to be dollars per hour. Rise is dollars. That's my output variable, dollars. Run is my input. That's hours. So my units are dollars per hour. So he charges $20 per hour. That's my variable cost. Hopefully you have quite a bit of knowledge about linear equations at this point from 111-95 classes. All right, let's talk a little bit about scatter plots. The way we're going to talk about scatter plots today is we're going to look at an example of some data of times of women's 100-meter winning times at the Olympics. So scatter plots are used to display data, usually data that has an input and an output value. So in this example, our input is the year. So this is going to go on the x-axis or the independent axis. And our output is the time of the winning women's 100-meter freestyle at the Olympics, this is going to be on the vertical axis or output axis. Now, when we look at this data right off the bat, we can see that if we go ahead and plot this, we're going to not start X until 1,912. And that's not usually convenient when we're using mathematical models or looking at graphs. So a trick that we do a lot is we readjust the input data. So I'm actually going to have X be equal to years since 1912. I'm going to kind of scale everything down to 1912. So instead of putting in 1912, I'm going to graph 0, 82.2. And instead of graphing 1924, that's 12 years later. And 32 is 20 years later, 40 years later, et cetera, just going down. So that's 48 years later, et cetera, ... I'll let you guys fill these in. So now I have X values that start at X equal to 0. And this is a way to focus a little bit more on the data. Now I'm going to go to Desmos and graph this data. All right, here's my Desmos. And to do a scatter plot like we want to do, we need to put the data in a table. So you go to this plus right here, which is add an item, and you're going to choose table. And you're going to put your X values in here and your Y values in here. So my first X value was 0, and my first Y value was 82.2. 0, 82.2. The next X value was 12, and then 72.4. All right, go ahead, take your time, go put your values in Desmos, pause the video, and come back. All right, are you back? Does your data look like mine here? That's great. If we want to zoom in a little bit on the data, a student showed me this button, which I didn't notice before, which is Zoom Fit, and it gives you a really nice view of the data. So this is our scatter plot for the data of years since 1912 on the X and winning times for the women's 100-meter freestyle on the Y. Scatter plots can give us linear patterns. So when we look at our scatter plots, we want to decide if the data looks linear or does not look linear. If the data looks like our first box, you can almost draw a line. Oops, that's not what I meant to do. You can almost draw a line and say, oh yeah, that's a linear relationship. It looks just like a line, and it's positive because the slope of this line is positive. It's going up from left to right, walking up the mountain. You can also have negative linear associations. If you were to draw a line that best fit in there, it would go down from left to right, and it definitely looks linear. But then there is the option of, data may not be linear, and you can't really figure out the trend here. Like you could draw lines, but none of them really are following the trend of the data. Let's take a minute and go back and look at our data and see if we can decide if it has a linear trend or not. So if we look at our data that we put in Desmos, I feel like this data does have a linear trend, a negative linear trend. It's going down from left to right. All right. All right, so now that we know how to do a scatter plot in Desmos and identify linear patterns, let's go ahead and start making some models. So we're now just sliding into like 12.3 and 12.5 sort of at the same time. Once we have our scatter plot, we're going to use a computer to compute, to compute a linear regression. I can't help myself from fixing this while you guys are watching this video, sorry. This is going to be a line of best fit that models the data. Now, of course, like what I was doing before, you could just draw a line in, but the computer is going to do the best job to minimize the possible error. It's going to give you a linear regression equation that will be in the form y equals mx plus b. So we're going to use our data that we've already done our scatter plot for to compute a linear regression. So here's the data again, but you should still have that in your Desmos. Hang on, let's go ahead and open up Desmos again. All right, so here's my data. Just like before, I haven't done anything differently to it. And now I'm going to compute a linear regression. Well, I want the computer to know that I'm referring to the data values in this table. So I'm going to use y1. If you just type y1, it does y subscript 1, and it says 11 element list, so it knows what it's talking about. And then we're going to use the tilde to signify that we're not doing equals. We're not saying this is exactly a linear equation. We're saying, hey, find us a good one that is close. And then we use m x1 because x1 referring to this x1 data column plus b. And the Desmos now will find us values of m and b that make a line of best fit, a line with the least amount of error. And when we look at this, it tells you that M is equal to negative 0.275603 and B is equal to 76.4779. All right. If you want to plot your residuals, you can. I don't recommend doing that. I wish I hadn't done that. In fact, I don't know how to undo that. I'll leave it for now. And these are going to be the values that you use in your equation. So we're just going to come back and write in that for M and write in that value for B. So remember, for M, we got negative 0.2756. Remember, this is the slope, and its units are always output units divided by input units, or y-axis units over x-axis units. And in this case, on the x-axis was years, and on the y-axis was seconds. So the units are seconds per year. So what does that mean? It means in the context of the problem, the times for the winning women's 100-meter freestyle Olympics are decreasing by 0.2756 seconds a year, all right? Decreasing because it's negative. Our B value was given to us by Desmos as 76.4779. So what this is saying is, in the context of the problem, the model has this as our starting value. So at year 0, which was 1912, the model says that the winning time was about 76.5 seconds. The real value was 82.2, because remember, a model is just approximating our values. It's doing its best guess. It's not going to be perfect. And this is what the model is starting at, the starting value for the model. So what do we do with this model? Well, we can use it to make predictions. We know that y is equal times, right? Winning times. And x is equal to years since 1912. So if we want to predict what was the winning time in 2012, we can just plug in 100 for x, because 2012 is 100 years after 1912, and predict what our winning time was. So we plug in 100 and compute it. We get 48.91 seconds. The actual winning time was 53 seconds. I looked it up. We could do this again if we wanted to predict what the winning time was in 2020 by plugging in 108. 2020 is 108 years since 1912. Plug that in and we get 46.71 seconds. The actual time that year was 51.96 seconds. So how good are these predictions that we're making? Well, first of all, let's talk about the vocab word interpolation. When we use regression equations to predict values within our given data range, it's called interpolation. So our data range was from 1912 to 2008. Any data value inside there, we can feel pretty confident about our model. It's not going to be perfect, but we feel pretty confident about it. Extrapolation is when we use a regression equation to predict values outside of the data range. We could go back before 1912, or we could go on past 2020. I think it was 2008 was our last one. So these predictions that we made for 2012 and 2020 were outside of our data range, and we feel a little less confident about that. In fact, we feel less confident the farther out we go. There's a couple things we can do to make ourselves feel more confident about our regression equations. The first thing we're going to talk about is the correlation coefficient, which is R. And there is the formula for R. You never have to calculate this by hand, so just thought you might enjoy looking at it. Here are some facts about R. R is always between -1 and 1. The size of R indicates the strength of the linear relationship between your x values and your y values. If the R value is close to 1, it's a strong positive linear relationship. If R value is close to -1, it is a strong negative linear relationship. If it is equal to 0, that means there is no linear correlation at all. It looked like that one graph that was just like a bunch of spots all over the place, right? That's what no correlation would look like. So if we looked at our example, our R value was negative, because remember we had a negative relationship and it was negative 0.915. So the data is a negative correlation, and it is very linear. Negative 0.9512 is pretty close to -1. The second value we're going to look at to decide how good our models are is the coefficient of determination. That is R squared. It's literally our R value, and you square it. It is usually expressed as a percent. So R squared represents the percent of variation in the dependent variable that could be explained by the independent variable. And 1 minus R squared represents the percent of the variation in the dependent variable that could not be explained by the independent variable. So in our example, R squared was 0.9047. So we say approximately 90% of the variation in the swim times can be explained by the variation in the year. All right, well, that's pretty much all of chapter 12.